In this sequence, we would like to discuss fully connected neural networks. Since this is the first type of network we will be looking at, we'll also discuss some basics that are common for all types of networks. The fully connected networks are typically the first type of networks that people look at, and these were probably also the first type of networks that were used. So there's some literature, there are other courses you can look at that also give an introduction to fully connected neural networks. Let's just start with thinking of the neural network as a black box. So, and we can say that the neural network computes a complex in the sense of a difficult function. So the input to the neural network is going to be a tensor, and the output of the neural network is also going to be a tensor. That means this could be a vector, this could be a matrix, this could be a tensor that has a higher rank. And why do we think that this is a complex or difficult function? So first, the input can be very high dimensional. If you think about images or videos, there are many numbers that describe one image or one video. The network itself has many parameters, so there will be many variables that describe the function that the network performs. This could be millions or even billions of parameters. Also, the output is often high dimensional, or at least medium dimensional. So, for example, in image classification, there could be 1,000 different classes. For now, let's make a simplifying assumption that the inputs, and possibly also the outputs, are vectors. This is a convenient simplifying assumption when discussing fully connected neural networks. And what we'll do is we'll keep in mind that other networks will have different types of tensors as input and output, but we'll just focus on neural networks that use vectors as input and output. So what are the different types of inputs that we are concerned with? There could be really multidimensional grids, such as like tensors, images, videos, volumes. Then we'll look at point clouds. Further, there will be graphs, and this is specific graphics. Interesting type of graphs are meshes, and we'll also have text. Text will not be dealt so much in this class, but it's one of the things to look at. So also we'll consider that n is quite large. Let's look at this notation again, just as a review. So the vector x written in boldface consists of multiple components, x subscript 1, that is a scalar, down to x subscript n, that is also a scalar. And you see this is not written in boldface, and we write that this x is an element of r to the power of n. Some words about functions. So we'll have a function denoted like this, f from r to the power of n to rm, and that means that this function has n inputs and m outputs. Of course, again, this is just a simplifying assumption to always talk about r, but the network could take integers as input, or maybe even as output as well, or there could be other types of input or output. Let's look at this example, image classification. So there would be a vectorized image as input and a vector of class probabilities as output. Let's say the images would be described by 1,000,000 values. Then we would have the images be million dimensional vectors, and they would be mapped into 1,000 dimensional vectors. Another concept is the idea of a linear function, and for now we look at the linear function that has a single scalar as output. So this linear function takes an n-dimensional vector as input and it maps it to a single scalar. And the linear function that we look at has this particular form. So f of this input vector x equals w1 times x1, that is some scalar parameter times the first component of the input vector x plus some other scalar parameter w2 times the second component of the vector, and so on and so forth. And at the end, we'll have a constant that is also a parameter of this function x. Note that we don't really distinguish between linear and affine here. We'll just call everything linear, irregardless if there is a constant in the end or not. There are multiple ways to write a function, and what I do is I use this term variables and parameters. So a function itself has variables and parameters. And there's different notation to distinguish between the variables and the parameters. So maybe I'll just go back to this linear function here. The input vector is this vector x, so the variable is this vector x, or the components of this vector x, and the parameters of the function would be this w1, w2 to wn, and the constant. Very often, if you do some simple mathematics, then you just omit the parameters. That is, you would write something like f of x equals, and then the parameters just show up in the definition of the function, but they would not be mentioned in the notation on the left. However, in machine learning, these parameters are important, or often more important, to keep in mind, because what we will see is then when we train neural networks, we will actually have to determine these parameters w, and then in fact w in some sense become the variables of the function, and maybe these input vectors will be treated more like a constant. So writing a function f x semicolon w means that this x is the input to the function and w are the parameters of the function. Now there could be more than one input, so there could be some x, comma, y, and then semicolon, w, comma, sigma, comma, whatever. So there can be more variables or sets of variables that are either on the left of the semicolon or the right of the semicolon. Other type of notation is the subscript notation, where you write f subscript w to denote that w are the parameters of this function f. This constant offset in linear function poses some obstacle to notational convenience. So if you had a linear function, it would be much nicer to write w transpose times x rather than w transpose times x plus some constant offset in the end. And the solution is to implicitly add an element 1 to every vector x. This is something in some sense similar to homogeneous coordinates that are used in graphics, in case you took a graphics course before. So what we have now is that this vector x that has components x1, x2, up to xn, so it's an n-dimensional vector, gets this additional component 1 that is kind of implicitly virtually added to it. And then for the vector w, the constant we write as w0, and now if we compute the inner product between x and w, so this function is now inner product, this is a general linear function where we have the constant w0 now in the beginning plus, and this is the same thing we had before for the linear function. So this is just a trick that simplifies the notation a bit. Very often when reading some deep learning material, it will not be totally clear which version is used, the one with or without the one. Typically, authors explicitly consider the offset W0 in simple equations and figures, but very quickly things get too cumbersome, and then these offsets are omitted in equations or figures to make things a bit more compact. We'll discuss two popular options for nonlinear functions. That is the sigmoid function and the ReLU function. For now, we'll look at this function with one input and one output. And these functions are typically computed element-wise. So the sigmoid function, sigmoid of x, or also written as this sigma of x, equals 1 divided by 1 plus e to the power of minus x. We can look at the graph, and at 0, we would hope that this is 0.5. And as the function goes towards infinity, it approaches 1. And as it goes towards minus infinity, it approaches 0. And it does so pretty quickly. So for sigmoid of 10, it's already greater than 0.99999, and sigmoid of minus 10 is greater than 0.0001. So if we're thinking about this as almost like a logical rounding function that is 0 when the value is small enough and 1 if the value is large enough, then if this value is going to be 1, 2, 3, it's already very high. And so it doesn't need to be very small or very large to approach 1 or 0. This is the ReLU function, and the ReLU function, ReLU x, equals max x and 0. It's a very simple function that simply clamps to 0 whenever the value is smaller than 0. So whenever the input value is smaller than 0, the output will be 0. And whenever the input value is greater than 0, then it will remain untouched. So ReLU of 7 is 7, and ReLU of minus 3 is 0. Just a reminder that very often we will, or almost always, we will talk about the vector version of this function. So a vector version of ReLU of a vector x is the same as max vector x 0, and the maximum here will be computed element-wise. Let's just imagine we have a 7-dimensional vector, then this max x 0 will go over each of the 7 elements of the vector, and for each one that is negative, it will clamp it to 0, set it to 0, and each value that is 0 or positive, it will remain untouched. We can build complex functions with simple building blocks, and that's the way neural networks go. So a building block is then going to be a simpler function, for example, a simpler function fi that takes a vector x as input and produces a vector y as output, or in the more general sense, maybe that takes a tensor x as input and produces a tensor y as output. So which are suitable building blocks to create a neural network? As you can guess, the three functions we looked at before, linear functions and the two nonlinear functions, sigmoid and ReLU, these are going to be great initial building blocks. Anything can be used. However, there are going to be some criteria, and the most important criteria to consider is that these building blocks have to be differentiable. So we'll look at the concept of a computational graph, and loosely speaking, a neural network is a type of computational graph. A computational graph is a directed graph where the direction of the edges indicate the direction of the data flow, and the nodes of this graph are the operations, functions, or variables. And the data travels on the edges. Let's look at a simple example. We have a function with 2 inputs and 1 output, y equals f of x, y equals x1 plus 3x2. So the input is a vector with 2 components, x1 and x2, and the output is a scalar. And now we can draw this as a computational graph where we have these input nodes x1 and x2. Then we have this node that represents the actual computation, y equals x1 plus 3 times x2. And then here we have another node for the output value. This might be fairly unusual way to draw this. There is some asymmetry in how neural networks are usually drawn. That is that the output variables are actually not drawn as separate nodes. Mainly the input variables are drawn as separate nodes. But we'll look at a lot of these variations. So now, again, these are actually variables or values, and only this node here is an actual computation. And so how we read that is that by these arrows, this x1 and x2 will be fed into this computational node, and then it produces this output that travels along this edge here. So just to give you some idea of the variations you have to expect, variables can be drawn as separate nodes or not. I personally do not like this because I find it is inconsistent. I would prefer if nodes only indicate computational nodes, but this is just not the standard. So typically people draw input variables as nodes, and then the computation as nodes, and not the output values as nodes. Then variables are sometimes drawn on the edges, sometimes not, and the output node is typically not drawn at all. Either way, you'll just have to adapt to whatever people show you, and you have to be cognizant of all these different design choices, how things are drawn and how they are presented, to make sure you understand what a particular author wants to show. So here's another version where I don't draw nodes or circles around the data. So we have one computational node, y equals x1 plus 3x2, and then you see that the variables x1 and x2 come in here, and then the output y leaves this computational node. Now this is another version that you will often see. So here the graph actually stops with the last computational node, which has kind of a dual function. It represents the computation itself, so y equals x1 plus 3x2, but it also represents the idea that this is an output value. So then x1, x2 are the input values, y is the output value, but at the same time it's a computational node that's computed like this. Okay, so just some ideas how these networks are drawn. One thing that is also an important choice is if the nodes are actually processing scalars or if they are processing tensors. So actually, this mainly relates to the output. So in traditional deep learning, each node kind of takes maybe a vector as input, but as output, it only outputs a single scalar value. And this leads to the overkill drawings that you saw up to, even a few years back, where the neural network drawings were just extremely complicated with tons of nodes and tons of edges. So for example, here we have a network that as a black box computes a function that has 4 inputs and 2 outputs. In this version here, we are drawing the last nodes here, y1 and y2, as orange, which these are still computational nodes, but they also basically the output of this node here is y1 and the output of this is y2. And these are the inputs x1, x2, x3, x4. And what you see then is here is one computational node that takes all these inputs x1, x2, x3, x4, and it outputs a single scalar. So this can lead to a lot of nodes being drawn. So and then these are typically called layers. So this is the input layer, this is the first hidden layer, this is the second hidden layer, and this is the output layer. Now, in a more modern introduction to deep learning, it is probably more customary to immediately start with nodes that have inputs and outputs that can be tensors, or in our initial introduction, vectors. So let's just look at this example here. We have a function z that is computed by the network that is a function of a, x, and b. And here we're actually mixing parameters and variables together. So we'll later see that traditionally this input is only this vector x. But here we actually have the weights of the network a and b that we also draw as separate nodes. All right. So the first step of our function, so we do the standard linear function ax plus b. So the first step, this is this computational node. It takes the matrix A as input and the vector x as input, and it computes y equals ax. And then this is the second computational node that computes z equals y, and y is the output of this node coming along this edge here, plus b, and b comes from this node traveling along this edge here, and then there could be maybe still an outgoing edge, and along this outgoing edge there would be this value z. This is a vector value that travels out. Now here along these edges there are tensors that travel. So here there's like a matrix that travels along this edge, and there's a vector that travels along this edge, and there's a vector that travels along this edge. So this is saves a lot of space and is conceptually probably also a lot clearer. So again, there will be different types of variables. So we look at this example, which is very similar to before. We want to compute a function z equals f of input vector x with parameters w and b. So what we do now is, instead of using a matrix A, we call the matrix W, because while in linear algebra the standard matrix name is A, if we talk about a neural network and weights of a neural network, the standard matrix name is B, W. So this function computes Wx plus B. And again, this is a matrix, x is a vector, and b is a vector. So x are the variables that travel along the edges and through the network, and wb are parameters. They also travel along edges, but these are parameters of the network. So there's a difference how these two types of variables will be treated when the network is either fully trained and is executing during runtime, or when the network is training. So during runtime, the input data determines these variables x, and the weights of the network, the parameters of the network, w and b, will be constants. So the network is fully trained, it ships now, w and b will not change. And any new data that comes in, any new vector x, will be processed with the same w and b. Let's contrast this with training. During training, the input data x, it will change all the time, and we'll do that for different x. But for computing this backpropagation, that will be one of the key ingredients for training. We'll discuss it later. The input data is more similar to a constant, and the network parameters w and b will be considered as variables that we try to optimize. So we will look at an optimization algorithm that will try to compute derivatives with respect to these network parameters w and b, and will, at each step of the optimization, will slightly modify these network parameters w and b to make them better and better. So during training, we actually consider the network parameters w and b as the variables. So if we draw a network, then what we actually would like to do is not draw these network parameters at all, to save some space and to make the drawings conceptually simpler. So in this example here, we redrew what was there before. So x is an input vector that is going to go into this node that computes y equals w times x. And here, there's no more node for this parameter matrix w. That's just implicitly assumed to somehow, you can imagine a virtual node here that has an edge that goes into this computational node. And then the output y travels and goes into this next node. And this next node, again, it has some parameter b that's like virtually, you just imagine it here, that has an edge that goes into this node. And then we give the color to signify that this is the output of this mini network. Okay, so this is a data node. Then we have this and this as two computational nodes. But now we can ask, what makes a node? You know, how do we decide what to put inside a single node, and when do we split and put computations in multiple nodes? So a computational node is also called a layer of the network. So this is not super precise terminology, and there's some history to that. We'll just use it very loosely for now, and we'll say that the computational node of the network is also called a layer. And the question then is, how complex should a layer be? I mean, in some sense, one could make the complete network and put it into a single layer, which of course will not be the winning strategy. So let's look, for example, at this linear layer that we kind of looked at before. It computes y equals linear x wb equals wx plus b. Should that be two computations, first wx in one node or one layer and then plus b in the second layer, or should all of that be in the same layer? And then the answer is that the linear layer computes exactly that as one computational node, as one building block. And this is important for implementation. Now, a layer is often drawn as a rectangle, and the height and the width of this rectangle can be proportional to the size of the output tensor of a particular layer. Let's look at this other drawing of what we had before. There's an input vector x and an output vector y, and then we have this layer L1 here that computes y equals wx plus b. Again, we don't have any edges or nodes relating to the network parameters w and b. And here we have a rectangle instead of a circle, and one, for example, could draw the rectangle to be higher if y has more dimensions, and one could make it smaller if y has fewer dimensions. So in a network that maybe network drawing where you see rectangles that get taller and taller and taller, this should signify that the hidden states, the dimensions of the hidden vectors, get to be larger and larger and larger. Then on the contrary, sometimes you see networks where the rectangles get smaller and smaller and smaller, and then this signifies that the actual hidden variables, the dimensions of these hidden vectors, get fewer and fewer and fewer. For images, as we will see later in convolutional neural networks, people sometimes use the height as well as the width of these rectangles. So for images, the height of such a rectangle is typically drawn proportional to the resolution of an image, and the width is often drawn proportionally to the number of channels that an image or tensor has that is processed by the network. So it is not uncommon to see networks that have rectangles that start out to be thin and tall, meaning that you start with very few channels but high spatial resolution, and then the networks and then the rectangles become smaller and smaller and smaller, signifying that the image resolutions get downscaled more and more, but the number of channels increases because the rectangles get smaller and smaller, but also fatter and fatter. All right. For nonlinear layers. So nonlinear layers work element-wise. So if you see something like ReLU x, or even ReLU can take in an arbitrary tensor, it just goes over each element and it clamps to 0. So whenever the element is smaller than 0, it would make it 0. Or analogously, sigmoid of x, sigmoid of a vector x, proceeds element-wise. It applies the sigmoid function to each element of the vector. There's this traditional term called activation function that also refers to these nonlinear functions. Now, in current programming, the idea is that these nonlinear functions are put into a separate layer. So you have one layer that really takes a vector or tensor as input and applies this nonlinearity, ReLU or sigmoid. So, for example, you will often see that there's a linear layer, as discussed before, and then there will be a separate nonlinear layer directly after it. So in the visualization, you might see that these nonlinear layers are drawn separately or they are omitted. So let's look at this one version here. So the input vector x goes into this layer L1 and produces this output y. But this layer here computes the nonlinear function ReLU of wx plus b. So this part inside the brackets would be the linear function, and this outside here is the nonlinear function. And if you see a drawing like this, that still means that in the implementation there would be two separate layers, one for the nonlinear function ReLU and one for the linear function inside the brackets. And the reason is just another simplification to avoid the drawings to be overly cluttered. But here's another version. Sometimes people maybe just draw like two boxes right next to each other. Then, okay, there's like a linear layer before, and then there's the nonlinearity. We'll also have convolutional layers are drawn in this way. There might be this convolutional layer and then the nonlinearity afterwards. So there are two boxes that makes it more clear that these are implemented as separate layers. And again, it would compute the same thing. Now, another version that is more rare, where people really split it up into two rectangles and draw edges between the two. So you could also have that. So where this L1 here is the linear layer, and then here this gray box is the nonlinear layer. All right. There's another bit of complication that is batch processing. The neural network will need to process data in batches or mini batches, maybe something we'll also discuss later. Just think of it now of a sequence or a set of input tensors or input vectors. So if the input to a layer or the network is a vector x, then a sequence of those vectors would be a matrix. So that means the layer has to be able to take a vector, one element, as input, but it also has to be able to take a matrix as input. So it has to be able to process a matrix of vectors as unfortunate formulation, a matrix where each of the rows or the columns is a vector that should be considered as input data of the network. All right, so we basically process a bunch of these input data at once. Now, there are lots of design choices. So data can be in columns or rows. You need to make sure that whatever deep learning package you use, you do the right thing. And now you'll have to be careful with transpose. So how will that change, right? Is it like ReLU of W times X plus B, or is it ReLU of X transpose W plus B transpose, or is none of these correct? So where exactly do you put the transpose and how do you put the order? This is something that you'll have to figure out when implementing neural networks. The other thing is you have to be careful with broadcasting. So we have something like W times X plus B is B added to the columns or to the rows. Again, this is some type of error you can make with regards to matrices, their transpose. So these things you hopefully can figure out by yourself. Also, just in general, if you see that and you took a linear algebra course, you might be shocked because broadcasting in general is not allowed in mathematics. There will be criticism that you're making a basic syntax error, but in computer science, this is actually allowed to add a vector to a matrix. So now we go to fully connected neural networks. A fully connected neural network is a neural network that consists of alternating linear layers and nonlinear layers. Another term would be multi-layer perceptron. Now, this is also one slight catch here. As a final layer, there's typically another type of nonlinear layer, maybe some softmax for classification, that we will discuss a bit later. So the catch here then is that you know how to build a fully connected neural network after this lecture, but you don't really know the last layer yet. Okay, so this is again as our drawing. Maybe there's an input vector x1, and so this is not to be confused with the first element of a vector. This is really a vector with many dimensions. This is just the first one of its type, and then the output of this layer will be x2. Again, this is a vector, this is a vector, this is a vector, and so this vector x1 comes into this layer, and then this type of drawing has this linear and the nonlinear layer drawn as one layer, and this computes the nonlinearity ReLU of W1 x1 plus B1. All right, so now the parameters also have to have subscript to distinguish between the parameters of this layer and this layer and this layer. And then, so we have here W1 and B1 are the parameters of this layer. And then here we have W2 and B2 are the parameters of this layer. And W3 and B3 are parameters of this layer. So now this would be called a 3-layer neural network, even though another way of counting the implementation might count 6 layers, because each of these boxes is a linear layer and a nonlinear layer together. However, it's customary not to talk about nonlinear layers when saying how many layers your network has. So for a fully connected neural network, one would only count the linear layers if you say how many layers your network has. Then in the future, when we also will have convolutional layers, it will also be customary only count the convolutional layers as layers when someone talks about the number of layers. So then networks will have mix of convolutional and linear layers, and then we'll count both of them, but we also don't count the nonlinearities. All right. And let's discuss more broadly different types of neural networks. What we saw here are feed-forward neural networks. And there's a different type of network that would be called recurrent neural network. So what's the difference? In all these computational graphs that we saw, the data was flowing along edges, but there weren't any cycles. So a recurrent neural network has cycles. That means directed cycles. If you follow the data flow along edges, it's possible to walk along a path and end up at the same node that you started walking. This is not possible for feed-forward neural networks. The data passes through the network once, and there's no feedback mechanism. Another term would be deep feed-forward networks for feed-forward neural networks. And by contrast, a recurrent neural network, of course, has these feedback connections. There's something else going on. The recurrent neural networks have a slightly different way of accepting data. It's typically data that's in a sequence where you don't know how long the sequence is. So types of blocks. All right. So another term first, a fully connected neural network is also called a multi-layer perceptron. And the fully connected network generally only uses fully connected layers. That means linear layers. Then another dominant network is called convolutional neural network that uses predominantly convolutional layers. And the network that uses mainly convolutional layers and a few fully connected or linear layers, this will also be called convolutional neural network. So we'll do some history here, maybe to look at some more details. That is, traditionally, many people build these neural networks using neurons that output only a single scalar value. We'll now look at this alternative, and it helps to make some details a bit clearer, but I hope you will also see why this has gone a bit out of fashion, because then it becomes too complicated too quickly. It becomes very difficult to draw, it becomes very difficult to write, and it becomes very difficult to find variable names for all the many different variables that are needed. So this whole idea comes a bit from this neurological research, when people said, oh, these neural networks are going to be built a bit like the brain, so we'll call one node that outputs a scalar, we call this a neuron of the computational graph, and this combines a linear function with a nonlinear function. Okay, so now this neuron has many inputs but only one output. So that's what's different now. Only one output versus vector-valued nodes in the computational graph. So one example would be, this is a sigmoid combined with a linear function, and this is a ReLU combined with a linear function. So again, the input is vector-valued, so you see e to the power of minus, this is a vector W transpose x, and then the sigmoid function applied, or here you see the same with ReLU. So just to make sure, this maximum is now not the vector maximum, this is really only the maximum of a scalar, because this W transpose x gives you a scalar, and so the input is vector valued x, but the output is scalar valued. And then this nonlinear function again is often called activation function. Yeah, just one thing, and then the output of such a neuron, or specifically the output of the activation function, is then often called the activation. Okay, this now is an example of a single neuron that produces a single scalar as output. This is the neuron, this is a node of the computational graph. It computes this function f that has an input vector x, and it has parameters w. So there are three inputs, x1, x2, and x3, and it has this one scalar output, y. Just as a reminder, if there are three inputs, x1, x2, x3, there will be this virtual x0, and there will be four parameters. So three of the parameters are weights for x1, x2, x3, and one of the parameters will be a constant offset. Okay, skip. Now this is an alternative drawing that highlights the kind of the idea that a lot of deep learning was rooted in neurology and trying to model the brain. This is not so much the case anymore, at least not for implementation or a modern introduction. There's still a lot of work related to that, trying to model the brain, understanding the brain, and trying to build networks that behave similarly to the brain. So either way, so back in the day, the neurons would be drawn like this to make it kind of look like they're that the computational nodes are actually neurons, so you call the cell body, and then the cell has these two parts. It has the linear part here, and then it has the nonlinear part here, so here you compute the linear thing. It's a sum of wi's and xi's plus the constant offset, and then this is whatever the nonlinear activation function is, and then you get one output here. And so then these things, you can even use the names from the brain, you know, like axons and synapse and dendrite. Now, this you can also look up if you're interested in it, but I think to me the key concept is that by deriving the whole thing from the brain, it becomes more logical or to actually marry this linear function with the nonlinear function in a way that leads to neurons that have only a scalar output. And then this leads to a lot of complexity. So again, so what's the real difference? Here we will compute, again, we have a lot of inputs, but we'll only take one output, and then for this one output, we compute this one linear function, this one nonlinear function. But in the modern implementation, you actually compute a lot of linear functions, creating a lot of linear outputs, and then for all of these outputs, you compute the nonlinear function at once. So here's this drawing of this mini network. We have an input layer, layer 1, where we have 3 values, x1, x2, and x3. And then here we have the layer 2. And so what is this A subscript 1 superscript 2? This refers to the output of these neurons or computational nodes. So in fact, again, this thing has a linear part and a nonlinear part, and this is the output of the nonlinear part that leaves this cell and goes then into the next cell. So this subscript 1 means this is the first component of this layer, and the superscript 2 denotes the layer. Again, so A3 means this is the third component of the layer, and this superscript 2 means we're talking about layer 2. Then you can guess that A1 means it's the first component, the first output of layer 3. And this can also be actually done for the input layer. So instead of saying x1, it's kind of the first input, this could be called A subscript 1, first component, superscript 1 of layer 1. We'll also have a weight matrix to describe how we go from layer 1 to layer 2. And if you go from layer 1 to layer 2, the weight matrix will have a superscript that is based on the layer it comes from. So it will be W matrix W superscript 1. And the weights, so this neuron here has all of these variables will go in here, and they will have weights that will be described in the weight matrix. So let's look at these computations. So we'll stay here. So what is the, for example, the A12? So how is this computed? So we go into the weight matrix, and we'll first compute the constant offset by taking element W101. So that means the element in the element 10 of the weight matrix that has the superscript 1, that is the weight matrix describing how you get from the first layer to the second layer. And then what we have is this inner product between the, so basically this whole thing is the inner product between the W vector and the X vector, and this is just written out, this inner product. This is the nonlinear function, whatever it is, maybe ReLU or maybe a sigmoid. And so we see that here are all the parameters in the weight matrix written out. So how many entries does the weight matrix W superscript 1 have? Well, we can count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So more generally, if a network has Sj units in layer j and Sj plus 1 units in layer j plus 1, so this would be a 3 and this would be a 3 as well, then this weight matrix will be of dimension Sj plus 1, that means 3 times 3 plus 1, 4. 3 times 4, so we have 12 entries. Just a general word of warning, these weight matrices all have a different size. So they're not compatible and can't be put into a larger tensor. So while this weight matrix might be of size 3 times 4, then the other weight matrix, the next one, that goes from here to here, will have a different size. You can maybe pause and try to compute it by yourself. So how many entries will we expect? Well, we will expect 4 entries. 1, 2, 3, 4. And again, you will, if you just parse this by yourself, you will see the structures in a product between this one W vector and A vector. And so here this A vector will be corresponding to these activations drawn here. So we have A12, A22, A32, and what you see here is again this virtual activation that is set to 1 that will be added virtually, that will be multiplied so that you get this constant offset. All right. So now what we want to do is, we'll skip that, we'll look at the vectorized implementation. So what we do first is we say that the first activation vector A1 is simply the input vector x. Then we will add this virtual 1 in the beginning, and then we compute an intermediate output of the second layer, so that's not shown here. So if we're here, we compute this intermediate output, because each of these nodes now represents the linear part and the nonlinear part, so this is the output of the linear part. So we'll compute all these outputs of the linear part together by computing the matrix vector product, taking the weight matrix W1 times A1. Then we will compute, we'll do this nonlinear computation by taking the vector, so this actually should be a vector, as input and compute the nonlinearity for each element, and then we get the output of the second layer denoted by A2. Again, we need to add this virtual 1. We compute another matrix vector product to get the linear part of the last layer, and then we compute this final output. All right. So this concludes this sequence. I'll just maybe add another example to make this more clear, but this example is a bit easy, so this can easily be skipped if you're already well familiar with neural networks and fully connected neural networks.